Here is video 1 of chapter 6. Chapter 6 is on the structure of atoms, understanding really the layout of electrons. So here, a lot of what we know about the atom is using electromagnetic radiation and light waves. So radiation is any energy that is traveling through space in the form of waves. Some radiation we can see and some radiation we cannot see. And here's the spectrum shown here. And you can tell there's this small little portion of visible light that is energy and light waves that we're able to see in distinct colors. All radiation, no matter what type of radiation you have here, they all travel at the speed of light, which is 3.00 times 10 to the 8th. And I'll go ahead and mention that there is an equation sheet posted on Moodle that is for chapters 5 and 6. It's also the last page here. I'll show you really quickly. And it has the different constants and formulas we'll be using. So for example, right here is speed of light, little c, and it's 3 times 10 to the 8th meters per second. So here's several different types of radiation. You go from gamma rays, which is the highest energy radiation that you can, that's recorded on this spectrum, and radio frequency being the lowest energy. And they all are different size waves that correspond with the amount of energy. So down here we have really high wavelength, which we'll talk about in a second, and really low frequency. On the other side, we have really low wavelength, really small waves, and really high frequency. We'll talk more about that as we go. So wavelength, what it is the distance between two consecutive peaks. So I've kind of identified it here on this red wave. A wavelength can be from one peak to another peak, or even one valley to another valley. It's just two consecutive waves at the same point in that distance. So it's a distance, which makes its units make sense. They're usually in terms of meters, and one of our most common prefixes to use is nano. That's because our visible region, the light that we can see, has wavelengths that are in the nanometers. Here's a conversion you'll want to be really familiar with as we go. Is 1 times 10 to the negative 9th meters is 1 nanometer. That goes back to just the prefixes. That's what nano stands for, is 10 to the negative 9th. Wavelength, its variable is this lambda. It's kind of like a backwards H a little bit. And then frequency is the amount of waves passing a certain point in a given amount of time. So remember, all waves are moving at the same speed, at the speed of light, but based on their wavelength, it'll determine how many peaks pass you per unit of time, normally per second. So our 5 waves passing you per time, or our 10 waves passing you per time. The units for frequency are a little bit different. They are per second, so you can write them like this, where it's 1 over second. When a unit is on the bottom, you can bring it to the top of a fraction by taking its exponent and making it negative. So right now, this is normal seconds. You could write this fraction as seconds minus 1. And then seconds minus 1 is also known as hertz, which is abbreviated HZ. So these 3 units are used interchangeably. And the variable for frequency is this little cursive V here, a nu, another Greek symbol. So we want to get aware of those as well. So here, if you look at these 2 waves, you'll notice this one has a shorter wavelength. This one has a long wavelength. And then frequency, if you just think logically, if they're both passing you at the same speed, up here, this short wavelength, you're going to get more peaks passing you. And so that means that it has a higher frequency. And the opposite is true here. The longer the wavelength, the less peaks are going to pass you, meaning low frequency. We have an equation that helps us with that relationship, and it's shown here. C, which is speed of light, so 3 times 10 to the 8th, equals lambda times mu, which means wavelength times frequency. We have to be real careful with our units because speed of light is in meters per second, which means wavelength has to be in meters, can't be nanometers, and frequency has to be in seconds minus 1 or hertz, because that's putting seconds in the bottom. So that when you multiply these, it ends up being meters per second. This also shows me that when frequency goes up, wavelength is going down, and vice versa. So they have an inverse relationship. Here's an example of a problem. What is the frequency of radiation whose wavelength is 450 nanometers? So what we first have to do is get into the correct unit. So we take nanometers, I showed this down here, and convert to meters. Remember, nano will come to the bottom to cancel. 1 times 10 to the negative 9th on the top. You multiply, and you get 4.5 times 10 to the negative 7th. This really was only 2 sig figs, so this should just say 4.5 times 10 to the negative 7th. That 0 is not a significant 0. So here's our meters. Once again, I would X out that 0. And we know the speed of light, so we can divide in order to get our frequency. And I did use the correct sig figs in our frequency. Our answer needs to be in only 2 sig figs. So 6.7 times 10 to the 14th. And I wrote seconds minus 1. I also could have written hertz there. So that's how we can calculate frequency from a given wavelength. So here, to understand the energy associated with wavelengths, we can look at what's called the quantum mechanical theory. What it tells us is that waves are characterized by wavelength and frequency. We know that. Energy travels as packets known as photons that travel with the wave. And that we have a few equations we can use to calculate the energy of a wave. So if a wave has a set wavelength, it also has a set energy. Those two things correspond to each other. Same with frequency. Frequency can also be used to calculate energy of a wave. So those 3 variables can be calculated from one another. Here is one equation for energy. Energy equals H, which is Planck's constant. H is Planck's constant. It's listed here for you. And the units are joules times seconds. And then it's H times nu, which once again is frequency. And I just reminded you of that here. Another version of this equation is if you replace frequency with speed of light over wavelength from our earlier equation, then we can get this equation over here, which is energy equals Planck's constant times speed of light. We know both of those values over wavelength. These are both on the equation sheet. It just depends on what you have. If you have frequency, use this first equation. If you have wavelength, use the second equation. Once again, we got to be really careful with units because of our constants. So, and because energy is in joules. So frequency will need to be in hertz or seconds minus 1. And wavelength again will need to be in meters. So here it says an AM radio station broadcasts at 1010 kilohertz. Find the energy of these photons. So this time I'm given hertz or kilohertz, which means I'm given frequency. So I'm going to choose the equation E equals H times nu so that I can just plug in frequency and get energy. Well, we know H is Planck's constant, so that goes in as H. Frequency, however, has to match this seconds right here, which means it's got to be in hertz or seconds minus 1, same thing. So what I'm going to do is calculate from kilohertz to hertz, which just means I multiply by 1,000. So we multiply by, or divide by 1,000. Oh, it's multiplied by 1,000. I made a mistake here. So I need to go back and update this problem. We will multiply by 1,000 so that this will actually become 1.01 times 10 to the 6th. I will update this in the notes. So this is a good lesson to say. It's always good to write out conversions if you need to. So multiply by 1,000. This hertz value is off. I will update that. And therefore our answer is off. But this does walk you through Planck's constant times frequency. We got to make sure it gets into hertz correctly, preferably, and then we'll get into our joules. Okay? That'll be updated on the guided notes filled in. Okay, next, the red line in the hydrogen spectrum has a wavelength of 656.4 nanometers. What is the frequency and energy of the photon? So here we start with nanometers, which is wavelength, but we've got to convert that into meters before we do anything. So we take nanometers, we put nano on the bottom, 10 to the negative 9th on the top. Here's our meter value. Now we can plug that in to our equations. Then we can come over here and use the C equals lambda mu. We've got speed of light. And we now know our wavelength in meters, so we put that in. And then we're going to be able to find frequency. And frequency right here should be nu. I used the wrong variable. So our nu here is equal to 4.57 times 10 to the 14th hertz, okay, because of the leftover seconds here. So if this is our frequency, even though I used the wrong variable here, this should be frequency, we can now hop over here, use frequency to determine energy. So energy equals Planck's constant times the frequency that we found in hertz. So we multiply the two, you'll see seconds cancels with hertz. That's because hertz is 1 over seconds. So we're left in just joules, which is an appropriate unit for energy.